系，是礼拜的演讲。那我们今天很高兴邀请到东海大学那个张学新教授来帮我们做演讲。那张学新老师他的专长是在那个3个 component system 的那个旅行波的存在性跟稳定性这样。那一般就是做方程的话，反应扩散方程的话，2个 component 还 OK 这样。如果你到3个 component， 那就是变成一个很困难的问题这样。那张老师他在这方面有很深的研究这样，所以我们今天特地邀请他来做演讲这样。那今天因为刚好恰巧我们有一个国外的访客，那个 Emerson 教授在这里，所以张老师就会可能用英文演讲这样。好，那我们就欢迎他这样。
感谢蔡教授的邀请，这是我第一次在那个系上演讲。Okay, so my title is stability turing wave of some biological equation. Yeah, so the keyword today is stability of turing wave. The stability usually we call it local instability stability. So local means initially you make a small perturbation of the solution, and you want to ask for time large enough what's the situation? If it is close to the solution or not? Yeah. So because there are many students here, so maybe I talk something in ODE case first. So if you are familiar about the undergraduate course in ODE, you can know what I say. Yeah. So we consider ODE, which is U prime equal to capital FU. So suppose U0 is an equilibrium, therefore U0 satisfy, U0 is a constant satisfy this. So capital FU0 is 0. So in undergraduate course we say U0 is entropically stable. Okay, if phi t is the solution and the initial condition sufficiently close to the equilibrium, then for time large enough, phi t will tend to U0. Yeah, if satisfied this, we call it entropically stable. Yeah. So this is for ODE, right? And then the concept is very straightforward to use Taylor extension, right? Because we suppose the solution is a small perturbation of the equilibrium U0. So phi t is small, right? Phi is small. Okay, because phi is the solution, so you substitute this into here, you can obtain the left hand side phi t is Ct, and the right hand side is like this, and you consider Taylor extension like this. So small g is high order term. Okay, so capital F U0 is 0, right? And then you let this is a matrix A, capital A. So A is F prime U0. We usually call this the Jacobian matrix. So you can imagine that if P is very small, then the high order term small g, which is nonlinear term minus the linear term. Okay, yeah, this is a high order term until p squared, right? So it should be small enough. So consider this. You have a corresponding linearized equation, which is p prime equal to AB here. And usually we suppose solution phi t is like this, right? E lambda t multiplied a factor w. So substitute this into here, you can obtain lambda and the w. They are eigenvalue and eigenvector, right? So we know the stability of U0 can obtain by the linearized equation. If all the eigenvalues has 0 part not equal to 0. Sigma A is the collection of all the eigenvalues. So we suppose the real part is not 0, then we understand. If all the real part is then 0 of the eigenvalue, we obtain U0 is entirely stable. Okay, but on the other hand, if at least one eigenvalue has positive real part, then U0 is unstable, right? So we know this, right? So okay, this is what we know in undergraduate ODE case. So But now U prime equal to capital Fu. Capital F maybe a differential operator if we consider PDE, partial differential equation. So what is capital F in PDE? For example, the right hand side may be like this. If we consider reaction diffusion equations, right? So in this case, Uxs is the second derivative about the x variable, and the small fu is the nonlinear term. Okay, this is what we call reaction diffusion equation. And in general, this is a system of equations. So you have n components. Small f also has n components, and capital D is a diagonal matrix. This is a usual case. And this kind of reaction diffusion model includes many kind of biological equations. For example, the Lotka-Volterra equation, which consider the competition between many species, and also Fitzgerald-Nagumo equation. Fitzgerald-Nagumo equation consider the naive extent of the path. Okay, so for many this kind of equation, the pattern formation, the problem about pattern formation can be observed. For example, in this picture, this is the competition between three species in Lotka-Volterra equation, and the two pictures describe the higher dimension version of the Fitzgerald-Nagumo equation. Okay. In particular, we can consider traveling wave solution of a general reaction diffusion equation. So, in general, this kind of PDE is not easy to solve, right? So, we find a particular solution, like traveling wave. What is traveling wave? So, traveling wave in this case, the solution U has two variables, and we suppose it is dependent on a single variable function called capital U Z. The variable Z is x minus st. Okay. So this if solution has this form, we call capital U is the traveling wave solution. So usually S is the called traveling speed. S here, S is the constant. Yeah. And usually we consider condition and plus and minus infinity because the domain here usually we consider the whole space. The space variable is the whole real line. Okay. So we have boundary condition and plus and minus infinity. We suppose it tends to some constant capital U plus and capital U minus. Usually this satisfies the zero of the nonlinear term. Okay. So you can imagine what happens if time evolves. So for example, if t is 0, you can obtain the solution has profile which is capital Ux. Okay, suppose Ux has this profile, then you can understand as time evolves. For example, time equal to 1, it's just a translation of the profile at t equal to 0, and when time equal to 2, it translates 2s of this function, capital U, right? So you can understand. As time goes by, so the traveling wave keep the same shape and the same speed to move in a fixed direction. So all the traveling wave has this kind of feature. Okay, so if a partial differential equation is a traveling wave solution, then you can easily to find many phenomena. Okay, and mathematically, okay, you can put this n stuff into here. So this is a simple elementary chain rule. Okay, in like calculus, right? So small ut by chain rule you can obtain this is du dz partial derivative partial z partial t. Okay, partial z partial t is minus s. So here is minus s u prime, right? And similarly, u sub x equal to u sub z here. Okay, so the original PDE can be written like this form. Okay, left hand side is this, the right hand side becomes this. So this is the equation for traveling wave. In the most simple case, is we consider capital D equal to 1. This is a single equation. A small f like this. This is what people call the Fisher KPP equation. This is very famous to consider biologically in maybe from 80 years ago. Yeah. And the traveling wave answers like this. So you obtain the traveling wave equation satisfy this equation. And what people call wavefront. What is wavefront? Wavefront means you suppose u minus tends to 1 and u plus infinity equal to 0. So the profile looks like this. Okay. So people call this is wavefront. Okay. So this kind of wave exists for all s greater than or equal to 2. So usually people call 2 is the minimum speed. Okay. So this is called Fisher KPP wave. Okay. KPP is 3 people. Komogov, Pijovsky and Kuno. Okay. So this is a very famous example. So okay. So if U is a traveling wave solution, so it satisfies this equation. Right? Okay. So we consider the traveling wave equation depend on time. So we consider the original reaction diffusion equation in the moving frame coordinate. The moving frame is like this: z x minus st. So we obtain a PDE, which is a parabolic equation like this form. Okay. So we put the right hand side equal to capital Fu. So here capital F is right in this style. So by this star equation you can understand capital F capital U equal to 0 because we have this, right? So you can see U is the equilibrium of this equation, right? So so you can put the idea from ODE stability to PDE here, right? So the language is very similar to ODE, right? So if we want to consider stability of the traveling wave capital U, so you consider the solution of a small u of this, which is a small perturbation of the traveling wave. So V, you can consider V as a small perturbation. So similar to the idea of tidal extension, you substitute this into the original equation, so you can obtain the left hand side ut becomes vt. So because z is the independent variable of t. Okay. So right hand side like this. So like Taylor extension, you can obtain. It looks like this. So G, capital G is also the high order term. And here F prime U, we denote it is L. Okay. So L is what people call the linearized operator around the traveling wave. So L, the operator L looks like this form. Okay. And the high order term G should be small. You face small, right? So you can as I said, similar to the ODE case, you can obtain a linearized equation from here. If you drop the nonlinear term G here, so this is the linearized version. And similarly, you can suppose small v, which is E lambda t multiply a function wz here. So if we substitute this into the linearized equation, you can obtain. This is the eigenvalue problem of the linearized operator. And the lambda and the w, they are eigenvalue and eigenfunction here. Okay. So if you understand lambda, you can obtain the stability of the original traveling wave. Okay. So we can compare ODE and PDE version. So they look very similar, right? So in ODE case, you linearize around a constant. This is a function linearized around a constant. So A is a matrix. But now for PDE, the situation is a little different. You consider F here is not a function, it's an operator, but this is an operator linearized around a function. So L is a destination operator like this form. Okay. So because now in this case L is not a matrix, so it is a little complicated. What is the so-called eigenvalue? Okay. So usually in this case, for operator we consider we say all eigenvalue as the word spectrum. Okay. So usually there are many ways to divide define spectrum. Usually there are two kinds. The first one is if sigma L is spectrum, and sigma n is called the normal spectrum, which is isolated eigenvalue with finite multiplicity. Algebraic and geometry multiplicity, they are finite. So people also call it discrete eigenvalue. And the complement of the normal spectrum is called essential spectrum. So usually people also call it as continuous eigenvalue. So you can divide in the two kind of spectrum. So you can think essential spectrum is very complex, right? But there are some cases you can distinguish normal and essential. Usually, if lambda is a normal spectrum, the corresponding eigenfunction will decay to 0 at plus and minus infinity. Okay. So, but for essential spectrum, its eigenfunction will not decay to 0. It may be oscillate at a plus and minus infinity, like a sine cosine function, right? Okay. And there are something more about the spectrum of a linearized operator. Traveling wave is an important property people call translation invariance. What it is? If U is a traveling wave, then any translation is also a traveling wave. For any translate alpha, right? Okay, so in this case you can define translation as a translation operator, T alpha, like this. So T alpha is the operator. If it operates to U, it means you translate alpha amount. Okay, so because we already say capital Fu is 0, therefore any translation is also a traveling wave. So U with multiply on the translation operator is also a traveling wave. So this capital F with this also 0. Therefore, if you take partial derivative about alpha on both sides, you can obtain this. So if you take derivative about alpha, you can obtain you can obtain this, and this is what we call the linearized operator L, and the T prime 0 U is U prime U with derivative on Z. Okay. So this means U prime is a kernel of the linearized operator. Okay, in other words, we always have 0 is the eigenvalue of a linearized operator. So this is the main difference between PDE stability and ODE stability. So in ODE stability, you can suppose 0 is, if 0 is not an eigenvalue, then you can have stability. But in traveling wave, the stability of traveling wave you cannot avoid 0, because 0 is always the eigenvalue. So in other words, you always have center minimum. Okay. So there are many kind of definitions. This result is cited from a book by Captura. Okay. Usually we call the traveling wave is spectrally stable if its spectrum satisfies this kind of condition. Because you know 0 is the eigenvalue, but if furthermore it is the simple eigenvalue. Simple means the algebraic multiplicity is simple, and all the other spectrum lies in the with real part less than a negative constant. Okay, in this case, if spectrum satisfies this form, we say the traveling wave is spectrally stable. Otherwise, it is spectrally unstable. So spectrally unstable means there are eigenvalues with positive real parts. Okay. And what is linearly stable? Linearly stable means if it is spectrally stable, and moreover, the corresponding semigroup has this kind of estimate. And here P is the projection onto kernel L. Okay. So if we don't consider kernel, by this assumption, all the spectrum is which real part is negative. So it is straightforward that you should have this kind of estimate about the semigroup. If this is also true, with spectrally stable, then traveling wave is linearly stable. So, okay. So what is non-linearly stable? We can put this as that, because we understand any translation is also a traveling wave. So a good answer is you consider the small perturbation include the translation of traveling wave. So alpha is also a constant we need to find. Okay, so and U lies in some function space. Usually we consider function space is like capital S X, which is BUC, like founded a uniform continuous function. And the non-linearly stable is defined in this way. Okay, so we say the traveling wave is asymptotically stable with shift in this space. So if we consider this kind of PDE, we already see this previously. And U0 is the initial condition. So this terminology is similar to orbital stability in ODE, right? Because if the initial condition sufficiently close to the traveling wave, then the solution small UZT of this equation should have this kind of estimate for some translation of the traveling wave, and alpha 0 is some translation. Okay, so this is the time decay estimate. So in this case, we call U is established stable with shift. So similarly, established stable with no shift means there's no translation here. So if you can obtain this kind of estimate, we call it no shift. Okay. So with shift or not depend on 0 is eigenvalue or not. So in some function space, it is possible that 0 is not an eigenvalue. Okay. For radiation diffusion equations, if the traveling wave is spectrally stable, then it is established stable with shift. This is what of people call it in radiation diffusion equations. Spectrally stable implies non-linearly stable. So for radiation diffusion equation, if you know the information about spectrum, then you can have the non-linear stable result. Okay. So this is a very famous theory. Can be found in many elementary textbooks, for example, in Henry's book or Barbara's book. So, but for other PDE which is not radiation diffusion equations, in addition to spectrally stable, we also need L, the operator L, which is generate analytic semi-group if we want to consider linearly stable. So usually we need the resolving estimate like this form. Okay. So for if lambda is large enough, if we have this, then L is sectorial and generate analytic semi-group. This is similar to the Keller-Segel theory. So this is a general version of Keller-Segel theory. If we have this, then L can generate analytic semi-group. Okay, so we can write the linearized operator in this way. This is a generalized form. It is a second order differential operator, and the coefficient of the second derivative, first derivative, and this term can be written as capital DMN. Okay. There's a standard theory of essential spectrum. That means essential spectrum is very complex. You cannot find all the essential spectrum, but we don't need to find all the essential spectrum. We only need to find the boundaries of the essential spectrum. Okay. So if we can find the boundary, it's enough in usual case. So the boundary of the essential spectrum is determined by the spectral curve, like the blue curve here. Typically they like parabola for in this part. If lambda is very large in here, they like parabola. The spectral curves, they are S plus and S minus. It's defined like this. Okay. If lambda satisfies this equation, lambda belongs to the what we call spectral curve. And here, dmn here is we consider in plus and minus infinity for the three matrices here. And how to obtain this? It is not difficult, because if we solve the eigenvalue problem at plus and minus infinity, it looks like this. Lambda is eigenvalue, p is eigenfunction. So if you suppose eigenfunction p is a vector multiply ei tau z here, because you consider essential spectrum as we studied previously. So in some case, essential spectrum it may be oscillate for space larger. Okay, so because it's oscillated, so you can consider it is it looks like sine cosine here. Okay, so if you put this ansatz into here, you can obtain this. Because the second derivative has 2I tau drop down, so it is minus tau squared. So the first derivative has 1I tau drop down, so I tau is here. Okay, so usually P0 is not 0. So if we want to have a non-trivial P0, this determinant must be 0. So we obtain this. Okay, so this can be obtained straightforward by this answer. The essential spectrum theory tells us the essential spectrum will enclosed by the spectral curve S plus and S minus. So essential spectrum will be inside this region. Okay, so we call the blue curve as the boundary of essential spectrum. So this is the story about stability ansatz. So in the following, I show some examples I studied previously. Okay. The first example is the three-species Lotka-Volterra competition-diffusion equation. This is a general equation for the competition between three species. The three species, they are U, V, W. Okay, and the D1, D2, D3 is the diffusion rate. And the R1, R2, R3, they are the growth rate of U, V, W, respectively. And the Cij here is the competition rate. So if Cij is positive, means this is a competition system. Okay, we can suppose this system is a traveling wave. So the answer is the same. We did capital UVW is the traveling wave. This is the variable, the traveling wave. So we can obtain a system 3 ODE like here. And the boundary condition we consider is like this. So in minus infinity only V survives. In plus infinity only U survives. So you can realize in both minus and plus infinity W decays to 0. So W looks like a path. So UV they are front and back. Okay. People always ask there are some motivation about this boundary condition. So maybe it looks like this. I think so this is U. This is V. W is a path. Looks like this. Okay. So this is the profile of this equation. So this problem coming from a problem about a coexistence problem. So you can think the W originally there are two species UV here, and the W invaded into this system. Then you can ask if originally UV cannot coexist, after the invention of W, you can ask if W will change the original behavior. That means if UV can become coexist or not. So you can think W in phase. It will be W in phase into the UV system. Okay. So if W invades into the system, W can only survive in the place. U and V, they are not so dominant. So it's natural that W can survive only in the middle part. So in plus and minus infinity, UV they are very strong. So in plus and minus infinity, UV they are strong. So W cannot survive at the plus and minus infinity. Thank you. Yeah. So this is the reason why we consider this kind of boundary condition. If W equal to 0 in a three species traveling wave equation, if W equal to 0, you can reduce the equation to a two species traveling wave equation. It looks like this. So there are only two species. So we suppose U0, V0 is a two species traveling wave of this equation with boundary condition looks like what I plot in here. So in left hand side only V survives. In right hand side only only U survives. Okay. In one side only one species survives. This kind of traveling wave already studied by many people. This is stable. This traveling wave is stable. This is proved by Kang and Fang many years ago. So we can understand that if the third component W is 0, this is what people call the trivial three species traveling wave of the three species equation with this boundary condition. So you can think because W, if W is 0, it automatically satisfies the third equation. So we call it trivial. Trivial means W is trivial. And moreover, if W is totally 0, W also satisfies this boundary condition. Because in minus and plus infinity, W from 0 to 0. Okay, so this is trivial. Trivial three species wave. So there's a question. If U0, V0 in two species equation, we know it is stable. But if the two species is stable or not in a three species environment. Okay, so okay, so in many cases we can study. Some maybe people can think if the two species wave is stable, it should be stable, right? No, this is not always this case. So this is the first theory about the stability results. Some part of this work is coming from my PhD thesis. A joint work with Professor Chen, Hong Li-Tang, and Professor Miura and Ogawa. And Professor Ikeda also obtained a similar result, like in the following. So the key point here is we consider the two parameters here, C13 and C23 here. So there are two cases. The first case is C13 and C23, they are small. We consider the two parameters, they are small. So what is the meaning? The meaning is the influence of W is not so big about U and V. So people may think that W is weak in this sense. So if W is weak, UV, because UV is stable, so it should also be stable, right? But the result is not. Originally, U0, V0 is stable. If W is weak, people may think it is also stable. But this is not the case. If we have this condition, if this equation is a non-trivial solution, when C13 and C23 they are 0, that means we have a non-trivial W of the third equation. So although W is weak, if we suppose C13 and C23 they are very small, but if the third equation has a non-trivial solution, this means W is not so weak. Okay, so we cannot only suppose this to think W is weak or strong. So there are many other cases we need to consider. For example, there are growth rate and the diffusion rate. We also need to take into account. So, so in this case, W is a non-trivial part. If we have this, when the two parameters they are 0, then the trivial wave is unstable. This is case 1. Case 2 is different. Case 2 means, another case is different. Conversely, if the two parameters they are not small, then people may think W is strong, right? If W is strong, maybe it will change the original stability result. So people may think that the trivial will become unstable, but the result is not. It's not always true. It's not always like we imaginary. So if the two species satisfy this condition, this is artificial condition. But if this can be satisfied, then the trivial wave can be stable. So this is a condition for 0, 0, B0. This is a variational kind of inequality. Can be satisfied for all the test functions theta belongs to this Sobolev space. So if we suppose this bracket is positive, this result is true. Right? Okay.
So the star condition in general is very difficult to verify.
Yes. But I already checked. This can be achieved for some special U0, V0.
Okay.
Yeah. For there are exact solutions of two species Schrödinger wave, which can obtain this star condition. So this is non-empty. Okay.
And how about the speed of this trying wave compared with the speed of this two species stable trying wave?
Because all this is the method used is bifurcation, similar to bifurcation technique. So the particular speed is very close to the speed of two species. Yeah.
But you don't know because the first one is for small coefficient.
Yeah.
And the second one is for maybe not small coefficient. Okay.
Yeah.
So you don't know will be faster or it could be slower.
I understand your problem.
Yeah.
No, we don't know. Yeah. This is an interesting question. Thank you. Yeah.
Okay.
So I can talk about the 5 cup. So I think. So maybe I can show some sketch of proof. Okay, this is the condition under condition parameters. So maybe we can talk a little about this. If the two parameters they are not small, we suppose any two of the species they are strong competition. So this is the assumption of strong competition. So any two of the three species they are considered very strong. Okay. But if the two parameters C13 and C23 they are small, it is easy to see the two inequality cannot be satisfied because C13 is here, C23 is here. So if they are small, this is not true. So if they are small, we drop these two assumptions. So only U and V they are strong compared with each other. The sketch of proof is like this. People can check the trivial wave is bistable. Bistable means the equilibrium at the plus and the minus infinity they are stable. So the standard theory of essential spectrum tells us the essential spectrum will lie strictly in the left half plane, in the convex plane. So the real part of this then a negative constant. This can be achieved by compute the boundary of the essential spectrum, as I showed in previous slide. So. Like this, yeah. So this can be really write down. This can be write down for Lotka-Volterra competition system. So we can obtain the spectrum lies strictly in the left half plane. And the key point is what is the linearized operator. So this information includes all the stories. Okay. So we consider L to be the linearized operator around the trivial wave. And the eigenvalue problem LP equals to lambda P is UVW. So it becomes like this. So the three equation looks like this. So this disappears because this is 0. So we obtain this. So the key point, the key parameters C13 and C23 here. So if they are small, we consider they equal to 0 first. So if the two parameters equal to 0, the equation for UV and the W they can separate. So the first two equations only have UV. The final equation only has W. Okay, so it is easy to deal with. Okay, so because the two species wave is stable, so there is no eigenvalue with positive. There is no eigenvalue with positive real power for the first two equations. So the eigenvalue problem for the first two equations is already done by the previous result. And moreover, from the result by Berstiki, if the third equation of the traveling wave equation is coming from here, if the third equation has a non-trivial W, has a non-trivial solution, then the third equation has a eigenvalue with positive real part and a non-trivial W in here. Okay, so this is the reason why we have instability result, because this is the result directly coming from Berstiki. But all this can be done for the two parameters equal to 0. And our final goal is to consider they are very small, but this can be obtained by the perturbation theory of linear operator from Cato's book. Okay. So we have if they are 0, it is unstable. So if they are close to 0, it is also unstable. So it can be easy to realize.
Why the third equation is decoupled from the previous two?
Oh, because we consider they equal to 0 first.
I mean the third equation.
Yeah, because this is 0. If you linearize, this is a Jacobian linearized around this. Non-linear equation linearized around this. So because this is 0, so there are no UV here. So this is the situation about C13 and C23, they are very small. But on the other hand, if they are large, we cannot suppose they equal to 0 first. So this case is more complicated. So in this case, what we can only do is start from the third equation. Because in third equation there is no UV. So we need to deal with the third equation first. So, okay, so everything coming from here. And by the start condition, so we suppose the start condition. This condition is very strong. So from the start condition, we have this eigenvalue problem has no eigenvalue with real part greater than or equal to 0. So this result can be obtained. This is very standard because this is the scalar equation. By the theory of Stern-Liouville, we can obtain this result. So the third equation, there is no eigenvalue with positive or 0 real part. So we only need to consider the eigenfunction with 0 W component. So the eigenfunction we only need to consider like this. But in this case, if W is 0, then the eigenvalue problem reduced to two species linearized eigenvalue problem. So if W is 0, then the two components here, the two terms here disappear. No matter C1 and C2 is large or not. Okay. So if W is 0, put it into here, we obtain this. So coming from this part. But this is the standard result from the two species case because two species wave is stable, so the spectrum satisfies this structure. So we obtain the stability. Okay, so because three species equation is very complicated, so by consider some special case, it is possible to obtain the stability. I think my time is not enough, so maybe this part I can skip it more short because this is another case about Lotka-Volterra. But here the story is different. Here we put emphasis on C13 and C31, the two constants here. Previously we suppose all the Cij they are positive, but here conversely people can suppose the two constants they are 0 or negative. So if they are negative or 0, in this case U and W they are cooperative, and the phi computed with U and W. So people call this as competitive cooperative system. So both cooperative and competition behavior appear in this system if we suppose the two constants satisfy this. This system is very special because in this case the three species equation can be transformed into a monotone system. So all the theory of monotone system can be applied into this case. Okay, there's a famous result by Wu Jiahong and Zhou Xinfu. People can check from their paper about monotone system theory. Okay. So monotone means the nonlinear term F satisfy this monotone behavior. If we have an ordering of U and if U greater than V, then Fu greater than UV, like in this sense. So people want to find people can think it is possible to find the monotone traveling wave form. Previously, there are many people consider this. For example, if the two parameters they are small, they are negative, only some previously considered this case for some very special restriction on parameters. But recently, Professor Guo Dongzhen and Wu Chaohong and Wu Jingjing, they consider the two parameters they are 0, but their assumption on Cij and the boundary condition are different. But they all consider monotone wave front. The result by Professor Dongzhen Guo, they find the condition of parameter to achieve minimal speed by lattice dynamical system, but they didn't find the stability result. So we can use another method different from lattice dynamical system theory by the classical one, like a soup-sub solution technique, to find the existence of traveling wave form, and if you find the existence by soup-sub solution technique, then it is possible to obtain stability. Okay, but on the other hand, if you use soup-sub solution technique, it is difficult to find a minimum condition to achieve minimal speed. Okay, so no way is very good for all cases. The final result is like this. So the monotone wave form is like this sense. So in minus infinity it is 1, 0, 1. In plus infinity 0, 1, 0. So monotone waveform looks like this. So if these conditions are satisfied, then for all traveling speed S, this is traveling speed. If traveling speed is greater than this number is minimum speed. Then this equation has a monotone waveform solution, and this waveform is unstable in the bounded uniform continuous function, and instability stable with no shift in the weighted space x sigma. X sigma is the weighted space. The weight is 1 plus exponential sigma z, and the weighted norms look like this. The weight sigma need to satisfy some constraint. So if in this weighted function space, this wave is extremely stable with no shift. So the proof is very standard by the soup-sub solution technique and some theory of monotone system. So because this is very classical, so maybe I can skip the proof. Maybe I can skip the proof. Sorry. So the third example we obtained recently for the Keller-Segel equation looks like this. So this story is different from Lotka-Volterra. This is a problem about people call chemotaxis. Okay, so here U is the density of a species, and V is the chemoattractant concentration. V is the chemical substance. So here the diffusion of U depends on the gradient of V. So the constant chi here is called chemotaxis sensitivity. Chi is a constant, positive constant. So we suppose the U is influenced nonlinearly by the gradient of V. So if phi is a monotone function, okay, and for the equation of V, V is diffused like followed by this equation. So G, what is G? G is the we suppose G looks like a quadratic function. So there's a critical point beta. So for phi less than beta, G is decreasing, and for phi greater than beta, it's increasing. So it looks like a parabola. So in general, G is the degradation rate. So in previously, people suppose GV is linear. People call this as a minimum system in previous case. So here we consider G to be nonlinear. So here something also special, because there are two epsilon in here. In epsilon in here, we suppose the diffusion rate of the species U is very slow. And here, there's epsilon here. Why? Because if you divide epsilon both sides, and epsilon is small, so you can think phi t is very large. Phi t is large. This means the rate of change of the chemical attractant is very fast. This is an assumption. So in this case, our result looks like this. So this is a joint work with Professor Hong Hongkai and Huang Bozi and Chen Yushuo. Chen Yushuo is the student of Professor Hong Hongkai. Okay, so under above assumption, we have traveling path solution of Keller-Segel equation. Traveling path means in the boundary condition U plus equal to U minus. So if U is the path, then we call this a traveling path solution. So we can prove that this path solution exists, and this traveling path solution is spectrally unstable in the boundary uniform continuous function and the weighted space for all weight. So this unstable result is very, very strong, because in any weight, this wave is spectrally unstable. Okay, the traveling path solution, the existence can be obtained by a standard single perturbation technique. it is singular perturbation because we have epsilon in here. So the existence proof is very standard, and the linearized operator we can write down. So it is a little different from Lotka-Volterra, and we can obtain resolving estimate. Therefore, the linearized operator can generate a semi-group. And we consider also in weighted space, so we change the operator to be a weighted operator. So if we consider the weight, the weight of operation, which is operator T, like this. So the new operator depends on sigma looks like this. So if sigma is 0, L sigma is original operator L. So we can obtain a spectral curve stability like this. If epsilon is small and the tau is small. Okay. So by all assumption, G prime V plus is negative. So S plus is positive. So S plus has positive real part. So we have instability result. So in weighted space, we can also compute the spectral curve to obtain the essential spectrum. So by a tedious computation, we also have there are some elements in the spectral curve with positive real part. So we obtain a root of Tumblr. Okay. People in many cases fronts are stable, but path is not stable. Okay. In many cases we can obtain such kind of result. But mathematically for systems of equation, there is no general rule to obtain this root of Tumblr. Okay. So my talk stops here. Thanks for your attention.
老师跟同学没有任何的问题。好吧，你就好，any comment？ 没有，那我们再次谢谢一下张女生老师。